So in this video, we are going to talk about a lot of properties and definitions, as you can see, regarding arcs of a circle. Okay. So first, what is an arc? An arc consists of 2 points on a circle, and all the points on the circle needed to connect them by a single path. So if I have a circle like this, I pick 2 points on a circle, and an arc would be this. Right? This could be one of the arcs I could make. The other arc that I could make could be this. It was probably not the best color to choose, but yeah. So both of these are arcs, right? As long as they're connected by a single path on a circle, then it's an arc, okay? And the center of the arc is the center of the circle of which it is a part. So if I'm looking at this arc here, then that means that this is the center of that arc. And, and I drew an arc that is exactly half, but let's say I picked these 2 points instead. And this whole thing now is my arc, right? This is the center of that arc. Or, I could take this little arc here, and this would still be the center of that arc, okay? So that's what an arc is. Central angle, it's an angle with its vertex at the center of a circle. So if I take this and I draw like this, an angle, this is a central angle because its vertex is at the center of the circle. A minor arc is an arc whose points are on or between the sides of a central angle. So for a minor arc, I have something like this. This here would be my minor arc. Minor. And then a major arc is an arc whose points are on or outside a central angle. So then this whole thing here would be a major arc. Okay. A semicircle is an arc whose endpoints are on the diameter, or the endpoints of a diameter. So if I took a circle, right, and I do this is my diameter, it passes through the very center of the circle, and I drew this arc is a semicircle. It's a fancy way of saying it's half a circle. In terms of labeling these when we write them, we often write things like triangle ABC or segment AB, right? If you're doing an arc, you write it with a little arc over it. So if I wanted to write arc AB, it would look like that. One note here is, let's say I have something that looks like this. So I have 3 points. I have A, I have B, and I have X. Okay. The minor arc joining A and B, I would just write as arc AB because it's just this little piece here. But because I also have this major arc that joins A and B, I would write it instead as as AXB. Because that way I know it's A to B passing through the point X, so this is the major arc here. So basically, it's the same thing you do with like angles or triangles. If anything is looking ambiguous, the more information you can put in, the better. And always, put it in, X should be in the middle, it shouldn't be to the side, because otherwise you're creating a different arc. Okay, good. The measure of a minor arc is the same as the measure of the central angle. So if this is right around 90 degrees, then the measure of this arc, we measure arcs in degrees. Lengths of arcs we can measure in centimeters or millimeters or units of length, but the measure of an arc, I say this arc here is 90 degrees. Okay, and the measure of a major arc is the measure of the minor arc, 360 minus the measure of the minor arc with the same endpoints. So if I want the measure of this arc here, I would just do 360 minus 90, and I'd get 270, and that would be the measure of my major arc there. Okay, so make sure you have all these definitions down, and you're comfortable with that, because we're going to use these words a lot. So let's look at our first set of examples here. Switch to blue. Okay, so example 1, I have a circle, I have an arc, I want to find the measure of arc ACB. Okay, so I want to find the measure of this arc here. Well, I know this is a major arc, right? And this is a minor arc. And if I want to find the measure of a major arc, I just do 360 minus the measure of the minor arc, and I get 340 degrees. Which all have degrees. Right? So I would have 340 degrees for this first one. I just do 360 minus that. For part B over here, I'm given the measure of XQY is 110 degrees, and I want to find the measure of XDY. So we do the same thing. We do 360 minus 110, and that gives us 250 degrees. Okay, good. So now we're going to go back and do some theorems relating to arcs of a circle. So here we go. Oh, one note first. This is important. Switch back to black. Note. Two arcs with the same measure are not necessarily congruent. And you can see why if we draw a picture. So if I draw a big circle, that's connected. If I draw this arc, let's say, is, I don't know, 70 degrees. Okay. Now, I'm going to draw another circle with the same center, and this arc here, which is 70 degrees. But is this arc congruent to this arc? You should be able to see that no, the arc on the larger circle is much, much longer than the arc on the smaller circle. Okay. So instead, we say two arcs are congruent when they have the same measure. So they're both 70 degrees. And, because we need one more condition, right? They have to be the same length. So they're either part of the same circle or congruent circles. Congruent circles. Okay. So that's just an important thing to keep in mind for you're talking about and think about congruent arcs and whether two arcs are congruent or not. Okay. So time for one of our theorems. So here's our theorem. In the same circle or congruent circles, maybe I should just type this. This is like slow. Congruent circles, any one of the following means each of the other are true. Okay? So here we go. The three things are congruent chords, congruent arcs, and congruent central angles. Okay, and I will show you what I mean when I say this. So I'm going to draw a circle. Actually, you know what? We have a circle drawer. Let's use our circle drawer. But we don't want an ellipse. We want a nice circle. There we go. Okay. So I have a circle. I'm going to draw, I don't know, two central angles. So let's say my center is here. So I'm going to have one line like this. And I'll have one line like this. And then we'll also do it somewhere else. So I'll do here and here. And let's say I tell you this arc is the same as this arc. Okay? If I say that these two things are the same, then we automatically know. So I said I have this has congruent arcs. This also necessitates that this must have the same central angle and it must have congruent chords. Okay? So anytime I give you any one of these, oh, I'm sorry. Oops. I'm drawing the wrong thing for congruent chords because these aren't chords, right? Chords connect a point on a circle to another point on the circle. I meant to draw, we need to draw a chord that connects the endpoints of my central angle. A little hard to see, but here we go. Okay, there we go. So, as I said, if you have congruent arcs, then you have the same central angles, and you have congruent chords, okay? So these are congruent, Okay, obviously all of these things, if we were interested in these are all radii, right? So all of those things are the same no matter what. We don't care about that. So that's the special thing. So if I take a circle and I'm like, hey, this chord and this chord are the same, then without any other information, you can say, oh, well, if those two chords are the same, this angle is the same as this angle, and this arc is the same as this arc. Okay? So any one of these things means that the other two are automatically true. Okay, so that's going to be an important theorem and it allows us to do a lot of stuff with it. So we're going to move to some examples that let us use this theorem, and you'll get to see how it is used. So here we go. So our first one, we're going to say that I have a circle B, it's centered at the point B, and D is the midpoint of arc AC. And what I want to do is I want to prove that BD bisects ABC. Okay? So it says prove, so I'm going to do a 2-column proof. So my first statement is just going to be the givens. So I know that I have circle B, and I know that D is the midpoint of AC, arc AC. And that is given. Okay? And what else do I know here? Well, I know that if this is the midpoint of arc AC, I know that arc AD has to be equal to arc DC, right? Because that's just what a midpoint is. So I know that this arc here equals this arc here. So that's going to be my second statement. So I'm going to say that arc AD is congruent to arc DC. And that's just, midpoint definition, right? Midpoint of an arc splits into two congruent arcs. Okay, so what else can I do? Because I'm trying to prove that BD bisects angle ABC. So I know that if these two arcs are the same, this is where my stuff from the last, what I was just talking about comes in. Because if these arcs are the same, then this angle has to be the same as this angle, right? If two arcs are congruent, then the central angle to those arcs is also congruent. So I can say that angle ABD is congruent to angle DBC because of our big theorem from the last page. And just keep in mind, if you're doing this in class, you can't just write theorem next to whatever you write. You have to write out the theorem that makes it true. I'm just doing this because it's a pain to write on this interface, but it's the theorem that we just talked about, where if two arcs are congruent, then all the other stuff is congruent. Okay, and then the last thing we can do is now I can say, well, if this is the same as this, then that means that BD must bisect angle ABC, which is what we were trying to prove. So BD bisects angle ABC. Okay, and that's because I mean, if a ray divides an arc into two congruent angles, then the ray bisects the angle. So I'm going to put definition of bisect. Okay, and we've proven it. So you can see it's a pretty useful property to be able to use. It lets us prove some stuff that otherwise might be a little tricky to do. So let's look at two more examples here, and then we have one more after that. So for example 3, I have a circle centered at O, and I'm being told the measure of arc AB is 102 degrees. And I want to find the measure of angle A and the measure of angle B in the triangle AOB. So I'm looking for this angle here and this angle down here. Okay, so I know that OA has to be equal to OB, right? These are both radii. So OA equals OB. That's just something that I know. These are congruent because they're both radii. I'm doing kind of like a fast 2-column proof. I'm not going to actually 2-column proof this. So that means that angle A is congruent to angle B, okay? Because it's an isosceles triangle, right? And then I know that this arc is 102 degrees, so this angle has to be 102 degrees. So then I know that 102 degrees, all the angles in a triangle add to 180, right? So 102 degrees plus angle A plus angle B equals 180. But I know angle A and angle B are the same, so I'm just going to do 102 degrees plus 2 times the measure of angle A equals 180, and then I'm going to solve this for angle A. And when I do, I get that angle A is equal to 78 degrees, and that's also equal to angle B, because they are the same. Okay? Good. Number 4. What fractional part of a circle is an arc of 36 degrees in 200 degrees? So here's what this is asking. If I have an arc that is 36 degrees, then what fraction of a circle is that? And the way that you do that is you just do, for A, we just do 36 divided by, well, how many degrees are there in a circle? There's 360, right? So 36 over 360 is 1/10. So it is 1/10 of a circle. And for 200 degrees, we do it the same way. 200 divided by 360 is equal to, 5/9 of a circle. Okay. Actually, this is also part A. And then part B, find the measure of the arc that is 7/12 of its circle. So we're kind of working the other way here, right? So instead of saying 3/6, our thing over 360 equals whatever, here I know what my thing over 360 is. I know I have 7 out of 12. So I'm just going to do 7 out of 12, but I'm multiply that by 360 degrees, right? I want 7/12 of the 360 degrees in a circle. And that gives me the measure of the arc that is 7/12, which is 210 degrees. Okay. We're going to do one more, do a 2-column proof one, example 5 over here. So here's our setup. You can see this is a little complicated. We have circle P and circle Q, centered at P and Q. I know angle P is congruent to angle Q. So I'm going to say this is congruent to that. And I know that line segment AR is congruent to line segment RD. So this is the same as this. And I want to prove that AB is congruent to, or arc AB is congruent to arc CD. So I want to show that this arc here is congruent to this arc here. Okay? So I know these two angles are the same, right? So if these two angles are the same, the two arcs have to be the same if the circles themselves are congruent. So I think what we really want to do here is we want to first prove that circle P and circle Q are congruent. And if we prove circle P and circle Q are congruent, then that automatically proves that these two arcs are congruent because the central angles are identical and are congruent. Okay. So let's set up a 2-column proof to try to prove the congruency of these circles. So first, I'm just going to list out some of the givens. So 1, I have that circle P is centered at P and circle Q is centered at Q. That is a given. I'm also going to list that angle P is congruent to angle Q. And that is also given. Okay. So if that's true, what can I say about that? I can say that line segment RP has to be congruent to line segment RQ. Right? And that's because of the isosceles triangle kind of principle, where if two angles are the same, that means that the opposite sides have to be the same as well. So I'm going to say that RP is congruent to RQ. And this is because if you have two angles that are the same, then the sides must be the same. Okay. Then I'm going to list my last given, which is line segment AR is congruent to line segment RD. Because now what I'm going to do is I'm going to prove that PA is equal to DQ just by subtraction, right? So this was a given. So for 5, I'm going to say that AP line segment is congruent to DQ line segment. And that's because I can just subtract, right? Because what I'm doing is I'm saying, well, if PR is congruent to PQ and AR is congruent to AD, then if I subtract AR from PQ, then I get AP. And if I subtract DR from QR, then I get QD. So then AP and DQ must be identical. Okay? So now we're really close, because now what I can do is I can say, oh, these two things, right, if these are congruent, these are the radii of the circles. So if the radii are the same, the circles are congruent. So I can say that circle P is congruent to circle Q because radii are the same. Radii are congruent. And then that proves our thing, right? We said we needed to prove the circles are congruent. So now I can say that arc AB is congruent to arc CD because of our theorem, our big theorem of the day, which, you know, if you were doing a quiz or test or in your homework, you would need to write out that theorem, right? Or you can shorthand it, but you can't just write theorem because there are a lot of theorems in the circles unit, okay? So there you go. That's how you apply the theorem, and you can do some proofs that maybe look a little complex, but if you just take it a step at a time, it's not actually that bad. Thanks for watching.